The Sun. This star governs all life on Earth, but that doesn't make it any less mysterious and terrifying. Huge solar flares erupt on our star. They send a phenomenal energy into space.
Flares can be the equivalent of millions of atomic bombs exploding in the Earth's atmosphere, all within a few minutes.
The effect of these solar storms can be felt from millions of miles away on Earth, and the consequences can be devastating for our technology. On the ground, there's a blackout. No more phones or internet, and soon, no more electricity. This scenario occurred in Quebec in 1989, and every day we grow increasingly vulnerable to the vagaries of the sun.
As we become more and more technology dependent, we really need to know how it works and to be able to predict events like this.
We can avoid the worst if we get to the bottom of these mysterious phenomena. That is the mission of two space probes. One is European and is called Solar Orbiter. The other is American and is called Parker's Solar Probe. The summer of 2018 marks the start of this crucial voyage, which will end up 4 million miles from the sun, closer than ever.
It isn't just touching the sun, it's also helping to protect life and society.
The images that we're going to have that close is going to be unlike anything we've ever seen.
Solar scientists have waited 60 years for these space missions. That's how long it has taken for engineers to invent the technology to withstand such a hostile environment. And the risks are high, even now.
It's the work of a lifetime, and it could be pulverized in a fraction of a second.
Spacecraft shield will be over 1,000 degrees centigrade. So it's like being in an oven.
A voyage to the gates of hell on a solar odyssey that is crucial for the future of humanity.
As soon as I saw my very first images of the sun, I was just mesmerized. I couldn't believe how much was going on. And then I started hearing about how little we actually knew about the sun. Then I was hooked. I was like, you know, this is something that I really want to try to understand.
The sun is fascinating and very mysterious. To truly understand it, we must attempt the impossible and touch a star. For almost 20 years, NASA and the European Space Agency have been pooling their efforts in order to rise to this challenge. Having landed on a comet with the Rosetta probe, and having caught Pluto on camera with New Horizons, we are finally about to travel to the heart of our solar system.
It is kind of our last place to go and explore, and I would say the most important place for us to go and explore.
With the European Solar Orbiter mission and the American Parker Solar Probe, a 60-year-old dream is about to come true. The notion of solar probes dates back to 1958. And, as is often the case in the history of science, it all began with a revolutionary intuition of a young scientist.
In 1958, a young scientist called Eugene Parker published a paper where he actually predicted that this solar wind, this continually streaming atmosphere away from the sun, would exist.
Young Eugene Parker's discovery was earth-shattering. Without observing a thing, just by using mathematical equations, he worked out that the sun must expel minuscule particles of matter. All the time, and in every direction. This solar wind reaches the whole of the solar system. Eugene Parker changed the way humans view the cosmos forever.
We realized that space wasn't empty, but there were particles streaming full of energy, and so immediately it became clear that to understand this, we probably needed to go close to the sun.
1958 was the start of the space age. Sputnik 1, the first ever satellite, had just been sent into orbit by the Soviets, and the Americans already had some catching up to do. 1958 was a decisive year for the American space mission. Its first breakthrough came in February with the launch of its first satellite, Explorer 1. In July, President Eisenhower created NASA to oversee America's space program. In the wake of the Cold War, the race for a space odyssey began. That same year, scientists from the brand new American Space Agency dreamt up the best possible space missions.
A committee was put together, chaired by John Simpson and James Van Allen, and they were asked to provide guidance and advice to NASA. They came up with 14 missions that they said they're the best things that we could do.
One of the 14 priority missions the Simpson Committee came up with was, of course, a moon landing, which later became the Apollo program. There was also the premise for the Mariner missions, which was to land on Earth's neighboring planets. And another of these 14 projects was the solar mission.
The idea was to go and observe the sun from close up, to get as close as possible to the sun. This mission has been a holy grail for most solar physicists ever since.
We actually have to go there to sample the composition of that atmosphere and the solar wind to fully understand it. And that is important because what happens on the sun impacts us here at the Earth.
13 of the 14 missions dreamt up by the Simpson Committee have become a reality in the ensuing years.
One small step for man.
Only one has yet to see the light of day, the solar mission. Engineers have faced an insurmountable challenge: how to build a probe that could withstand such a hostile environment.
So close to the sun, it becomes very, very hot. So it's like being in an oven.
And we are going to be moving through there, working and getting our data. We can't switch off, we can't avoid it, we need to go in there to take our data.
If you had an ordinary material sitting there, it would sort of it would fuse and evaporate very, very quickly.
It has taken 60 years for technological breakthroughs to make the space pioneers' dream a potential reality. To accomplish this feat, engineers from the two missions, Parker Solar Probe and Solar Orbiter, have had to construct super-resistant shields that could withstand the infernal heat. They have rivaled one another in ingenuity, inventing new technology, and sometimes rediscovering materials previously used by cavemen.
We really pushed the boundaries.
It was always designed just at the frontier of what was possible technologically.
It's not just engineers who have been working hard to get close to the sun. This project is finally seeing the light of day, thanks, in part, to the tenacity of solar scientists in Europe and America. Milan Maksimovic has kept the notion of a solar mission in mind for 20 years.
There have been several studies. I myself researched the possibility of a solar probe with Marcovelli. We've been constantly pushing for this mission to take place.
And finally, at the beginning of the years 2000, it seemed that this was actually going to happen. We had a dinner with Milan Maksimovic, whom of course was a good friend of mine back from the days in the observatory in Paris. And we said, well, maybe we are the ones that are actually going to be able to do this and see this mission through.
But scientists soon realized that a single probe would not suffice to solve all the mysteries of the sun. They would need two. First, there was the American Parker Solar Probe. NASA's probe is the closest to what space pioneers envisaged in the 1960s. It was named Parker as a tribute to Eugene Parker, the man whose revolutionary discoveries had inspired the mission 60 years previously could finally contemplate his ideas coming to fruition.
It was a tremendous honor to be able to introduce Gene to the spacecraft, to actually turn to him and say, Parker, meet Parker, and watch just joy and overwhelming come across his face. And he was very gracious. He kind of joked with me, gee, I just wrote a paper.
In his paper, Eugene Parker predicted that a critical zone must exist at a distance of 4 million miles from the surface of the sun in our star's vast atmosphere. This enigmatic region has remained a source of fascination for scientists for 60 years. It is the target of the American probe.
4 million miles, that sounds quite a big distance. But the Earth and the Sun are 93 million miles apart. So if I put the Sun and the Earth on a meter stick, solar probe would be just 4 centimeters away from the surface of the Sun, and that is close.
To get that close to a star without being irredeemably sucked into it, Parker's solar probe would have to be launched into space at considerable speed. NASA has had to come up with a twofold launch, using the most powerful rocket at its disposal, the Delta IV Heavy, with a takeoff thrust of 8 Boeings.
It is an enormous rocket. We need such a big launch vehicle so it can throw us away from the planet.
The secondary rocket is the one that sends it into interplanetary orbit, and will be moving at about 120 miles per second. And it will be by far the fastest spacecraft ever created.
After just 5 months, the American probe will approach our star for the first time. In order to get inside the strategic 4 million mile mark, it will have to keep circling it, getting slightly closer each time round. In December 2024, after a 7-year mission, before it dissolves in the 2 million degree heat, Parker's solar probe will do a final analysis of our star's atmosphere. The NASA probe won't be able to relay images of the sun from a furnace that hot. No telescope would be able to look a star in the eye from that distance without being blinded.
Solar probe will get so close to the sun that at this distance you simply cannot fly a lot of optical instrumentation. So this is something Solar Orbiter will provide.
So it can take images that will prove invaluable for scientists, the European Solar Orbiter probe will have to keep a distance of 26 million miles from the sun. It will need 3.5 years to complete this voyage. The trajectory of Solar Orbiter is very strategic. It will allow us to discover hitherto unexplored territory, in particular the sun's poles.
Solar Orbiter will not be as close to the sun, but its unique orbit, along with its suite of instrumentation, gives a much sort of more global picture of this fundamental physics.
The Solar Orbiter mission will also last 7 years before being abandoned in space. But just like Parker's solar probe, the European probe will have had time to collect essential data that will be transmitted to Earth in just 15 minutes. The results of the two probes will then be coordinated to give scientists around the world a better understanding of our star.
For us, this is a golden opportunity to have the two missions up at the same time and working together. The missions are very similar in what we want to do, but the methods that we're using to do it are very different.
One technical element in particular will be very different in the two missions. The heat shield situated at the front of the probe. That is the key to the mission, but also the main obstacle engineers have been coming up against since the 1960s.
If the heat shield fails in any way, then the inside of the spacecraft is going to start to heat up. And our instrument and our satellite, if it gets too hot, then they will just stop working.
The slightest fault in the heat shield would signal the end of the mission. For each of these two probes, the engineers have had very different issues to overcome. For Parker's solar probe, they have had to create an ultra-reflective shield that would survive being closer to the sun than ever before. The European Solar Orbiter probe will get a bit less hot, but its shield must be ultra-fine so that it can be pierced to make openings for the instruments without it being weakened in any way.
You protect very well, and then you leave a small leak and this destroy the isolation.
In Turin, the aerospace manufacturer Thales Alenia Space has taken 6 years to perfect the heat shield for the European Solar Orbiter mission.
Electronics are a bit like human beings. They work well at an ambient temperature of somewhere between 20 and 50 degrees centigrade. We have had to produce a shield that is just a few centimeters thick to protect our instrument from this intense heat. It's been a big challenge.
The engineers for Solar Orbiter spent a long time selecting materials capable of withstanding such an inferno. They have an exceptional instrument at their disposal for test purposes, a sun simulator. The exact conditions for the mission are reproduced in this tank. Firstly, the void, but also, more importantly, the heat and solar radiation. Before being selected, each material is tested to see if it is fireproof.
We make sure they don't disintegrate at high temperature. So we do a lot of sample testing of these materials in small quantities, and from that we extrapolate then the properties of the big surfaces on the spacecraft.
We tested the sample, failed, changed the material, failed again, made another sample, and this time was successful and selected.
In 2012, a solution was finally found for the European Solar Orbiter mission. Its shield is formed of two large panels, each measuring 2 meters by 3, placed 20 centimeters apart. The front panel is composed of 20 very fine layers of titanium. The back panel is made of carbon fibers. The titanium structure reflects some of the intensity of the sun's rays into space. The rest hits the second panel. The heat bounces between the shield's two panels before being expelled into space through the side openings. To make it even more effective, a unique covering has been created especially for the mission. It's called Solar Black. And against all expectations, the engineers had recourse to a pigment previously used by cavemen.
Solar Black is made from burnt bone charcoal. Interestingly, this is the same type of material that prehistoric man used to paint on the walls of caves. And this is a really stable substance. It won't be oxidized. It will still be pristine at the end of the mission as it is at the beginning.
Parker Solar Probe shield is quite different from that of its European counterpart, because the thermic challenges faced were even greater. The American probe will dive into an atmosphere that reaches temperatures of 2 million degrees, and it will get closer to these powerful solar flares than ever before. But at 2 million degrees, no metal can remain solid. The mission is only achievable because the sun's atmosphere is very unusual, quite different to anything ever experienced on Earth.
The sun looks like fire and it looks like there's lava coming out of the sun, but in fact it's not exactly that. It's not like a bunch of material. And actually at that point the atmosphere and the corona and the material that's flying away from the corona is actually not very dense. So there aren't very many particles.
The sun's atmosphere is billions of times denser than the Earth's atmosphere. The particles there are extremely hot, but they are also far too small and widely dispersed to burn the probe. The real risk for the Parker Solar Probe is the sun's rays, like the ones which warm us on Earth. But at that distance, the rays are 700 times more powerful than they are here. The temperature of the shield will rise to 1,400 degrees. That's cooler than 2 million degrees, but it's still intense.
1,400 degrees is already hotter than the melting point of most materials. The ovens you get in kitchens today reach a maximum temperature of 300 degrees. So where we're going to be sending our instruments is really extremely hot.
To find a material which can withstand 1,400 degrees Celsius, the American probe's engineers took their inspiration from space shuttles. So that they can survive their return to the Earth's atmosphere, their nose is covered with carbon-carbon, a composite material with exceptional thermic properties. The shield on the Parker Solar Probe has ended up being covered with a spotless white coating to make it more reflective. But the materials haven't been the only challenges for the two missions. They also need to be piloted with extreme precision, because the instruments need to remain protected by the heat shield at all times.
If the probe goes even slightly out of alignment, some of the instruments might get burnt and destroyed.
By the time we could get a command to her, it would be too late. She has to be able to look after herself. What happens if she starts to tilt? How do you correct that tilt? And all that has to be programmed into the spacecraft, and she has to do all that herself.
Total autonomy is crucial for the survival of the two missions. But even if the probe is correctly orientated, the instruments on the Parker Solar Probe must at no point be directly facing the sun. The heat would be too intense. Meanwhile, the European probe Solar Orbiter will literally be able to see through its shield.
Once the engineers had devised a way to create the perfect heat shield, the scientists then wanted their instruments to look through it to see the sun, the whole point of the mission. So it has a series of doors in it, and we've had to work out how you can open doors, how long they can stay open.
Hidden behind one of these doors is one of Solar Orbiter's most impressive instruments, the EUI camera, which will send us spectacular and hitherto unseen images of the sun. It has a wealth of innovative features.
It's as if we're short-sighted and we are being given glasses so that we can see the sun's atmosphere much more clearly.
The images that we're going to have that close is going to be unlike anything we've ever seen.
These images are essential. They will help scientists understand these mysterious solar flares which threaten our technology. And they might save the Earth from a blackout. Because our star is unpredictable, these incredible phenomena which form on its surface are often beyond our wildest imagination. At the observatory in Meudon, several miles from Paris, as soon as the sun appears from behind the clouds, there is a rush to study it. It's been the same story every day for more than a century. First, the shed slides on its rails. Then a strange appliance appears. The mirrors are checked. The first, then the second. The sun's rays are then captured and analyzed by this spectroheliograph. This age-old technique remains the perfect complement to the high-tech solar probes.
Solar Orbiter and Solar Probe are both very short missions in terms of duration, whereas here, with the spectroheliography, we can study the sun in the way it's been studied for 110 years. That means we have this very stable reference, which allows us to compare observations.
1908. 110,000 shots of the sun have been archived in these boxes. This is the world's longest-standing collection of photographs of the sun. These glass plates reveal big black spots which appear or disappear depending on the day. For thousands of years, the sun was thought to be an unchanging star which revolved around the Earth. That all changed in 1610, when Galileo directed one of the first ever telescopes at our star.
From his observations of these sunspots, Galileo showed that it was an evolving star, which changed daily, and that these spots moved and were more prevalent on some days than others. He realized that the sun was, in fact, an active star, a living star, which changes every day, if not every minute.
Today, the best Earth-based telescopes provide us with spectacular images of the surface of the sun. We can see matter that is in a state of perpetual turbulence. These incandescent granules appear and disappear again in the space of just 8 minutes.
It's almost like boiling water, convection. So the stuff is coming up from below and it is creating these granular patterns.
It's like it's boiling, but in an unfamiliar way. It bubbles up in a way that's unlike anything we see on Earth.
This boiling matter is essentially hydrogen and helium, but not in the form of the gases found on Earth. At this temperature, they're in the form of plasma, the fourth state of matter.
Everyone is familiar with solid, like ice, water that is flowing, and then a vapor of steam when you superheat the water. If you continued to heat and heat, it would actually dissociate into what it's really made of. So it's made of ions and electrons, and that's what we call a plasma.
The constant movement of this plasma inside the sun creates a vast magnetic field, 1,000 times more powerful than the Earth's magnetic field. That's what causes these black spots to appear. The size of them is staggering. This spot could engulf the Earth 10 times over.
They appear black because the magnetic field is so strong in a sunspot that it basically inhibits the heat and the light to go across it. However, they're not black. If you took it away from the sun, it would appear somewhat bright. So that it's just relative to the very, very bright surface around it, you can't tell, and it looks black.
Also, in the sun's atmosphere, the magnetic field governs everything, including these solar flares. They are like magnetic storms.
Sometimes the magnetic fields interact and they create these explosions like solar flares.
The most powerful telescopes on Earth show us the surface of the sun and these huge black spots with amazing precision. But they are incapable of showing us images of the sun's atmosphere.
These superb images of the sun's corona, with its loops and its bright patches, which are evolving all the time, are impossible to capture from the Earth. Satellites are essential for observing these phenomena.
Going beyond what satellites are currently capable of, the engineers working on Solar Orbiter have devised an exceptionally high-resolution camera that will be able to capture solar flares and perhaps even discover hitherto unknown phenomena. In Odyssey, near Paris, Frédéric Orcher's team is in charge of one of the cameras on board Solar Orbiter.
We've been developing this instrument for 15 years, so we feel very emotional about it. We're going to see it on top of this rocket being launched into space. That's bound to be extremely moving.
This scientist also worked on SOHO, a satellite launched in 1996 that is still active today. Images captured by SOHO and its counterpart, SDO, have revolutionized the way we see the sun, finally revealing its mysterious atmosphere. Only telescopes based in space can capture these images because the sun's atmosphere is so hot that its light is invisible from the Earth.
A lot of the interesting things that the sun produces do not emit radiation in the light that we usually see, but emit radiation in the ultraviolet and X-rays, and that's absorbed by the Earth's atmosphere. So you have to go into space to be able to see the active sun.
These images are achieved using a precise ultraviolet spectrum. A bit like with a scanner, they reveal the actual structure of these flares. Magnetic loops constantly crashing into one another. But a single ultraviolet wavelength is not enough to capture everything.
The sun atmosphere has a lot of layers, and you can't really see everything unless you're viewing in different wavelengths, and so it allows you to see different layers of the atmosphere.
Depending on which layer you're observing, you observe different phenomena. And if we combine these observations using different colors, we can reconstruct the life of these structures, these flares, and see how they evolve, how they're triggered.
In order to capture each of these different sides of the sun, the camera on Solar Orbiter is equipped with extremely fine filters. Scientists will be able to go from one filter to another using this motorized wheel and reconstruct these solar phenomena in 3D to reveal all their secrets. And this image will be all the clearer for the fact that this camera has a resolution that is 4 times higher than on the best space-based telescopes such as SDO.
Solar Orbiter will be able to see about 100 kilometers of the sun, which is the equivalent of seeing a grain of rice from a distance of 2 kilometers.
Thanks to this exceptionally high resolution, Solar Orbiter might even discover previously unknown phenomena in the sun's atmosphere.
Every time we look at the sun with higher resolution, we see more things. And the reason is that the magnetic field is stratified and has structure at very, very, very small scales.
The unique orbit of Solar Orbiter will also allow it to film regions of the sun that have so far never been seen, namely the poles. Observing them could throw up a few surprises.
As we We've seen before from other planets, unexpected shapes of vortices can occur in the polar region. At the poles of Saturn, we find that there's a vortex, which has a perfect hexagonal shape. So we usually find things that are unexpected. It's very rare that we can predict what will happen in a region that we've never explored before.
The European and American solar missions will allow us to take a leap into the unknown. A greater understanding of the Sun will mean a greater understanding of the cosmos.
These two missions will really unlock a lot of the mysteries that we've been dealing with for decades now. And
it's a fascinating topic containing fundamental secrets that are useful to understand the universe as a whole.
These missions will go well beyond the surface of the Sun, helping us to understand the effect that this imposing star has on us. Our star might be life-giving, but it is also life-destroying. This is a crucial step in our search for extraterrestrial life.
What fascinates me is that we discover lots of new things every time. Knowing how the Sun works will allow us to ask questions, such as how does the Sun interact with other planets in the solar system? And on a larger scale, how do stars interact with other exoplanets, which exist close to us in the galaxy?
The Sun is our star, but it is just one star among billions of others. There are more stars in the universe than there are grains of sand on Earth. Some are smaller, but there are also some that are much bigger, supergiants, whose cataclysmic death results in huge clouds of gas and dust. These spectacular cloud formations then give birth to a new generation of stars. Being smaller, the Sun will end its life in a slightly less dramatic way. It is crucial to our understanding of the universe that we study our star, because it resembles so many other stars. Understanding our star will help us understand others.
Being able to study our star so close, up close and personal with Parker Solar Probe will allow us to know so much more about stars throughout the galaxy.
It's quite a special star. It has one clear advantage over the other stars in that we can observe it in great detail. Not only can we observe the light the Sun gives off, we can also observe the matter emitted by the Sun.
One of the main priorities for the solar probes is analyzing the matter that is expelled by the Sun. This is the solar wind Eugene Parker talked about in 1958 and which remains a mystery to this day. The Sun is constantly ejecting part of its atmosphere into space. These particles are found all over the solar system.
so it's basically this hot plasma that's expanding away from the Sun. It is like a wind in that it's constantly blowing away.
It's fundamental to understand how these streams occur, and the reason is that we are in that wind. We live inside the solar wind.
These particles of solar wind are infinitesimal, but they're expelled at a phenomenal speed. 930,000 miles an hour. It's a real cosmic bombardment that can have devastating effects.
Solar wind has a lot of power, even though it's very tenuous. It can blow away an atmosphere of a planet over a long period of time.
4 billion years ago, Mars was quite different to what it is today. A vast ocean covered half of its northern hemisphere. Its atmosphere was dense and could sustain life. But gradually, over millions of years, this solar bombardment has extracted particles from Mars's atmosphere one by one. The red planet has already lost 2/3 of its atmosphere, and it loses a bit more every day. Mars has become arid and hostile to life because of its own magnetic field.
If a magnetic field of a planet, which kind of protects the planet from this constant bombardment of the solar wind, if that's not strong enough, then the atmosphere is more exposed.
Luckily, The Earth's magnetic field is much more powerful than that of Mars. It acts like a shield, deflecting the solar wind. Only a few particles manage to filter into the Earth's atmosphere. We can experience this incredible sight close to the poles. We call it an aurora or polar light.
And those accelerating particles then hit the atmosphere, and they interact with the atoms there, and then that creates color. And that's one very nice effect of space weather, so I'm glad that we have that at least.
Today, scientists still know very little about the solar wind, and yet it is essential. The solar wind may generate breathtaking effects in the Earth sky, but on other planets, it might be able to destroy life. The wind created by these stars is one of the keys to extraterrestrial life, far from the solar system.
We want to study the solar wind because we want to understand the interactions between stars and their planets. That's important in the context of studying exoplanets. Can the planet have an atmosphere? Can that atmosphere survive the presence of the star? Is the atmosphere such that life might eventually develop there?
At IRAP in Toulouse, one of the most important instruments on the European Solar Orbiter mission has been built. It will go to the source of the solar wind to uncover its secrets. Particles of solar wind will enter the instrument through this narrow slit and can then be analyzed.
We have a system which counts them one by one. It can count up to 10 million a second. We will measure their direction and their energy. We will discover all of the characteristics of these particles emitted by the solar wind.
In order to build an instrument capable of precisely analyzing this phenomenon, the engineers have had to recreate the force of the sun on Earth. This latest generation particle beam weapon accurately reproduces the intensity of the solar bombardment.
The sun is constantly releasing matter. Both probes are going to have to withstand that, as well as being able to measure it, so it's a real technological challenge.
We'll be able to reconstruct really what happens, why the wind is generated, what happens to the gas as it moves out. So that's what we plan to understand.
But the solar wind is not the only matter ejected by the sun. There are also these terrible solar storms. They've got much more dramatic consequences for our societies.
You know, the constant solar wind is just the background wind or the background weather that's kind of always there. And so these solar storms you can think of in terms of like hurricanes.
Several times a day, the magnetic field on the surface of the sun becomes unstable. A violent eruption occurs. And the sun sends up to 1,000 million tons of incandescent matter into space. The energy produced is equivalent to 10 million atomic bombs in just a few seconds.
But what happens is that it's done very fast, very quickly, and it's very energetic and focused, so it gives a lot of energy to very few particles that can do a lot of damage.
If they're directed at Earth, they travel with the solar wind and they impact the planet. They can also wreak havoc with our technology.
A particularly violent eruption could create an unprecedented blackout. How would humankind react to a super eruption of this kind? Could the solar missions help us prevent such a catastrophe? In the 19th century, during the Industrial Revolution, humankind suddenly discovered the extent to which it is vulnerable to the wrath of the sun. September the 1st, 1859, saw the most violent solar storm of the past 5 centuries. Scientists refer to it as the Carrington event.
First, there was lots of polar lights, even as far south as the Caribbean, which is very unusual. And this was also the first time there had been an impact on human technology. This was the era of the telegraph, and in several places, telegraphists got massive electric shocks.
Ejected by the sun with considerable force, the solar particles managed to filter into the Earth's atmosphere at the poles. Canada and the United States were the first to be affected. The geomagnetic storm that ensued attacked anything that ran on electricity.
It was as if an enormous battery had been plugged into the Earth, leading to overvoltage, which happens on electricity distribution networks.
In 1859, the consequences of this super flare were limited because human technology was only in its infancy. But 2 centuries later, it has invaded every aspect of our daily lives.
We here on Earth are totally dependent on the vagaries of the sun. We rely on technology every day.
If the super flare, one like the Carrington event, was to happen today, and that could potentially be extremely chaotic.
In the event of such a solar storm, today the first victims would be the satellites, especially telecommunications satellites.
These particles would pass through the satellite and they could destroy the computer, which is the brain of the satellite, and render them useless.
Telephones, radios, the internet. Humans would suddenly find themselves deprived of any means of communication for several hours. In the airports, control towers wouldn't be able to guide the planes. In war zones, armies would no longer have access to GPS. A geomagnetic storm would also disconnect the electricity in a wide number of areas, plunging millions of people into darkness for hours on end.
It would require a lot of effort and a lot of money to restore the outages in such a big storm. And who knows what kind of reaction people would have if you don't have power. We've become so dependent on it, right?
In 1989, a medium-intensity solar storm caused a blackout in Quebec. The damage was such that power outages persisted 1 year later. But if a super flare was to occur today in the United States, the cost is estimated to be $2,000 billion. And that solar storm could happen without any prior warning.
For one that's what we call a super flare, it could potentially happen in the next few years. It may not happen for 100 years. It may not even happen for 1,000 years. We just don't know because we don't fully understand what drives such big flares.
A greater understanding of the sun is our best form of protection. In light of this risk, a new discipline has been invented: space meteorology. Forecasters will attempt to predict the passage of a solar storm in the same way that a cyclone is forecast on Earth. Thus, people could anticipate the storm and unplug everything that can be unplugged. But space weather forecasting is still in its early stages.
We have great models that we use that say, okay, we've seen this on the sun, and this is what we think it's going to do when it comes to the Earth. But there is a piece missing in these models because we've never been there.
The Solar Orbiter and Parker Solar Probe missions will approach the Sun so that they can gather this valuable information. Their complementarity is one of their greatest assets for space meteorologists. But for these missions to be a success, first we must solve the greatest mystery surrounding the Sun, a mystery that has been puzzling scientists for over 70 years. The mystery of the Sun's upper atmosphere, otherwise known as the corona. On Earth, we have the unique opportunity to observe the Sun's mysterious corona during solar eclipses.
Fortuitously, the Moon appears to be the same diameter as the Sun, so it hides the Sun. And when it hides the light from the Sun, the light from the corona appears.
The corona is a very odd atmosphere because it begins close to the surface, but then it extends extremely far away from the Sun.
The Sun is so big and powerful that it can hold the particles from its atmosphere a long way from its surface. the corona rises to a heady height of over 4 million miles. This is where the American Parker solar probe will orbit. It is also where the solar flares that are attracting all of this attention erupt.
The priority was trying to figure out how the solar corona works. The fascinating thing is why magnetic fields store energy, produce currents, and then produce these huge explosions. How does this occur? Why doesn't it just sort of leak out slowly? Why does the magnetic field hold on to energy and then release it in this dramatic way? We don't know how the corona is created.
The heat of the sun comes from its core, which is in a constant state of fusion. The temperature drops as the heat spreads to the surface. The surface temperature is just 6,000 degrees. But then an incredible phenomenon occurs. In the corona, the temperature suddenly rises to 2 million degrees.
That's hotter than the surface of the sun. It's about 300 times hotter, and that just shouldn't happen. You don't walk away from a heat source and get hotter, you should get cooler. But no, this atmosphere is superheated.
It is from the heat of this corona that the flares draw all of their energy. And this crucial piece of the jigsaw has been puzzling scientists for decades.
One of the most promising theories is that the corona is heated by a myriad of micro or even nano flares, which are constantly erupting all over the corona. If you want an analogy, it would be like trying to heat a house purely by striking matches. If you strike enough matches, often enough, you could do it.
While the camera on the European mission Solar Orbiter is trying to film these potential nanoflares, the American probe will dive into the corona to collect samples for analysis.
It isn't just basic science. The science that we discover will be used to better predict what the sun's impact will be on the Earth.
On Earth, it is essential for us to be able to anticipate these solar storms, so we can protect our technology. But there's even more at stake for our astronauts. Once they are in space, they are completely unprotected.
Here on Earth, human beings are protected by the Earth's magnetic field. But as soon as we start exploring space, we are no longer protected by this magnetic field.
If we want to send astronauts to Mars, to the moon, it's important to know what that space environment. We also have solar storms that can create issues for astronauts.
We now know that the astronauts on the Apollo missions were very lucky. On the 4th of August 1972, a powerful solar flare hit the moon, just 3 months before Apollo 17 landed on it.
The astronauts' health could have suffered. They could even have died in the minutes following the storm from a massive dose of radiation, equivalent to the sort of radiation doses you get from explosions in nuclear power plants.
For astronauts, the forecasting of solar flares is a matter of life or death. The International Space Station already has a special shelter where the crew can seek refuge in the event of an alert.
We must be able to warn them when it's time to go into their imitation sarcophagus, which will protect them from radiation. That is still one of the biggest obstacles to overcome when it comes to sending human beings to Mars or other planets.
The results we get from these solar missions might save the lives of future space travelers. But whilst it will be a while before humans can explore the solar system, these probes are preparing for their voyage to the Sun. Not far from London, Solar Orbiter is being assembled with the utmost care, because that close to the Sun, the slightest fleck of dust could be disastrous.
It can go so close to the sun, so it can get so hot. We have to take extra special care with the cleanliness because any small bits of dust or contamination would get so hot it could catch fire if we didn't have a super clean spacecraft.
We've envisaged every possible failure. We've had to envisage these failures because once it's in space, there'll be nobody to fix the problem.
Over the past few years, the tiniest element of each probe has been tested to check that it can withstand the most extreme conditions. Even big solar storms no longer faze scientists.
I'm often asked, are you not worried about a big solar storm? And I say, no, that's what we want to see. We're designed to see big solar storms.
The American Parker Solar Probe will be launched first in 2018, followed 2 years later by its European counterpart, Solar Orbiter. With the launch imminent, it's an historic moment for those who have dreamt of these missions for so long.
You develop a kind of paternal instinct with these probes. You consider them to be yours, and sometimes it's impossible to imagine the thing is actually going to fly.
It's going to be a big mixture of stress and excitement all during the launch. But right now, I'm starting to get a little nervous because it's actually going to happen.
After 60 years of work and hope, the solar probes are preparing to touch their star. Whether it is to spare the Earth from a blackout, to make interplanetary travel possible, or to find life elsewhere, their voyage is a major step for humankind.